In this video we talk about graphing techniques. So we're going to talk about stretching and shrinking, reflecting, symmetry, and actually in this context we may talk about even odd functions and translations. So let's start with stretching and shrinking. So first, let's talk about vertical stretching and vertical shrinking. Let's take an example of this. We want to work on f of x equals absolute value of x. So let's start with this example. We graph the function first, absolute value of x. This is y, this is x. And in the previous video we learned how to graph this function. So let's choose some values, 1, 2, -1, -2. If we substitute 0, we get 0. If we substitute 1, we get absolute value of 1 is 1. Substitute 2, absolute value of 2 is 2. So this is 2, 2. This is 1, 1. And substitute -1. Absolute value of -1 is 1. Substitute -2. Absolute value of -2 is 2. And then we graph this function. We connect these points. So this is the graph of the function absolute value of x, as we learned last time. Now what happens if we multiply this function by some constant that's greater than 1? For example, we multiply by the constant 2. This is greater than 1. We want to see what is the effect of that. If we multiply the whole function by 2, that means we multiply the y coordinate by this 2. And here we determined 3 points, and in most of the cases 3 or 5 points are enough, or to graph the function or to make the changes on the basic function. So let's graph this function. Let's determine these points. Now if we multiply this 2 by 2, we get 4, and the x coordinates stay the same. So this is 2, 4, and multiply 0 by 2, stay the same. -2, 2. Let's multiply 2 by 2, we get 4, so -2, 4. Now we graph this function. This is the graph of the function g of x, which is resulting from multiplying the original function f by 2. So what happens if we multiply by a number that's greater than 1? If we multiply by a function that's greater than 1, we get stretching on the vertical direction, or we get vertical stretching. As we can see, any point here on the curve of the graph of the original function absolute value of x will be stretched, or we get the corresponding point becomes greater than that point. That means we have stretching here. Now what happens if we multiply by a value that's less than 1? So let's multiply it by 1/2. If we multiply by 1/2, we multiply each y coordinate of the original function by 1/2. If we multiply this 2 by 1/2, we get 1. So this point is 2, 1. 0, 0 stay the same. -2, 2. We multiply 2, the y coordinate, by 1/2, we get 1. So this is -2 and 1, and then we graph the function. Now here what happens here is that this is the graph of h of x, 1/2 of the absolute value of x. So what we got here is shrinking. The original function graph is shrinking as we multiply by a value constant that's less than 1. But if we multiply it by a value that's greater than 1, this is stretched. This graph is stretched. So we can summarize this here. We can write, if we get a vertical stretching. If we multiply f of x by some constant that is greater than 1, and we get vertical shrinking if we multiply f of x by a constant a that is less than 1 and greater than 0. I mean from 0 to 1. Sometimes we get horizontal stretching or horizontal shrinking. So we have horizontal stretching and horizontal shrinking. In this case, we multiply the variable of the function by some constant. In case I, or in case 1, we multiply the whole function by a constant. Notice here we multiplied by 2 the whole function, and we multiply the whole function by 1/2. But when we are talking about horizontal stretching or horizontal shrinking, we just multiply the variable x by that constant. So if we have horizontal stretching, if we multiply the function, the variable of the function by a. Notice here we multiply the variable x by the constant a. We didn't multiply the whole function, just the variable. And here a is less than 1, and we get horizontal shrinking if we multiply this the variable of this function by a constant that is greater than 1. Let's take an example. If the basic function was f of x equals x cubed, if the function is f of x equals x cubed, we learned from the previous video how to graph this function. So let's choose some values. Let's choose 0. 0 gives 0. Substitute 1, you get 1. Substitute 2, you get 8. Let's consider this as 8. Substitute -1, you get -1. Substitute -2, you get -8. So we connect these with this curve. So this is the graph of f of x equals x cubed. Now let's multiply the variable by some constant. Let's first multiply it by constant that's less than 1. So I'm going to use this color. G of x equals 1/2 x cubed. So we just multiply the variable x by 1/2. We didn't multiply the whole function by 1/2. Now we can simplify. 1/2 cubed is 1/8 x cubed. So the function is 1/8 x cubed. This is as if we multiply the original function by 1/8. So that means we multiply the y coordinate of each point by 1/8. So let's multiply by 1/8. If we multiply by 1/8 each y coordinate, so 8 becomes 1. So this point becomes here 2 and 1. Multiply the 0, it stays the same. Multiply 1 by 1/8, we get this point here. So this is 1/1/8. Multiply -1, multiply -1 by 1/8, we get -1/8 here. And multiply -8 by 1/8, we get -1. So we get this point here. Let's connect them. So this is a graph of g of x equals 1/2 x all cubed. So multiplying the variable by the variable of the basic function by a constant that's less than 1, we get the graph stretched. So we have stretched horizontally. So we have stretching. As we can see, this function, this basic function, stretched horizontally, as you can see from here and from here. Now let's multiply the variable by some constant that's greater than 1. I mean, we can choose 2. So we multiply the variable x by 2. We get 2x all cubed, and that's 8x cubed. Now if we multiply x cubed by 8, that means we'll multiply the y coordinate by 8. So let's multiply this 8 by 8, that's 64, but we don't have enough room here so to graph this. So let's consider this point as 64. And as I told you before, scaling is not, I just wanted to show you the process. The graphs are not accurate. So this point is 264. Let's multiply 1 by 8. We get 8 here. So this point 1, 8. 1, 8 is the point, this point. And multiply 0, we get same point. And multiply -1 by 8, we get -1 and -8. Multiply -8 by 8, we get a point here, -2, -64. And then we connect them. This should be a curve, and from here so this is the graph of the function. This is a graph of h of x equals 2x all cubed. So if we multiply by a constant that's greater than 1, if we multiply the variable of the basic function by a constant that's greater than 1, we get horizontal shrinking. As we can see, the horizontal distance shrinked from here, and if we look at the original function is the black curve represented by the black curve, it's shrinked horizontally. Okay. Now let's talk about reflections. Reflection across axes. So we have reflection across the x-axis if we multiply the function by negative sign. So we just multiply the original function by negative sign. If we multiply it by negative sign, we get the graph reflected across the x-axis. So the point xy becomes x negative y. So the y-axis becomes negative, and if it's positive it becomes negative, if it's negative it becomes positive. And we have reflection across the y-axis if we change f of x, now this is the y is f of x, to f of negative x. We just changed the sign of the variable, so xy becomes negative xy. Here in this case we get a reflection across the y-axis if we just multiply the variable by negative sign. Let's take an example. So if the function is f of x equals square root x, let's graph this function. Now this function is defined for non-negative values, so square root of -1 is impossible. We choose some values. Let's choose 0, 1 and 4. If we substitute 0, we get square root 0, 0. Substitute 1, square root 1 is 1. Substitute 4, square root 4 is 2. So the graph looks like this, as we've seen from the previous video. So this is the graph of f of x equals square root x. Now first we want to multiply this function by negative sign, and that should give us reflection across the x-axis. So I'm going to use function g of x equals negative square root x. That means we multiply each y coordinate by negative sign. So this point, the origin stay the same. This point 1, 1 becomes 1, -1. This point here. This point 4, 2 becomes 4, -2, because we just changed the sign of the y coordinate. And if we graph the function, it looks like this. This is the graph of the function g of x, negative square root x. So if we multiply the function by negative, the function will be reflected across the x-axis. Now what happens if we just change the sign of the variable? Let's choose h of x equals square root negative x. We just changed the sign of the variable, not the sign of the function. So in this case we can't choose positive values for x. We can't substitute x equals 1, because x equals 1 gives square root of -1, and that's impossible. So we should choose negative values. So I'm going to use choose -1 and -4. So if we substitute -1, we get -1 gives square root -1, and that's square root +1, which equals to 1. So -1 gives 1. Substitute -4. You already have negative sign inside the function, and x is -4, and that's square root 4 equals 2. So the point here is -4 and 2. So the graph looks like this. Now this is the graph of the function h of x equals square root -x. So what happens here is that if we change the sign of the variable, we get the graph, the original graph, square root x, reflected across the y-axis, The next video will talk about symmetry, odd and even functions, and then we'll talk about